Early March, 1944, near Anzio beachhead, Italy. A German recovery crew from the Third Panzergrenadier Division worked methodically around a knocked-out M4 Sherman, serial number USA 3089472, that had taken an 88mm round through its engine compartment 3 days earlier. The hull was a write-off, but Obergefreiter Hans Mueller, a veteran mechanic with 2 years of Panzer maintenance experience, had orders to salvage whatever components remained serviceable. Mueller's hands moved to the track assemblies with practiced efficiency, expecting the usual wartime expediency he'd seen in captured Soviet equipment. Thin steel plates, minimal engineering, designed for mass production, with no regard for longevity. What he found instead would trigger a crisis of confidence that rippled through German armoured units across every theatre of war. The Sherman's tracks, even after sustained combat operations across the volcanic rock and clay of the Italian peninsula, showed wear patterns that shouldn't have been possible. The rubber track blocks, a design feature German engineers had dismissed as wasteful and unsuitable for combat conditions, retained their integrity. The track pins showed minimal elongation. The guide horns that kept the track centered on the drive sprocket were barely worn, despite the brutal environment. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. Mueller had spent months maintaining Panther and Tiger tanks whose tracks required replacement after distances that seemed impossibly short compared to what this American vehicle had clearly endured. He called over Feldwebel Ernst Richter, his platoon's senior track maintenance specialist, a man who had overseen track changes on everything from Panzer IIIs in France to Tigers at Kursk. Richter knelt beside the Sherman's left track assembly, running calloused fingers across the rubber blocks, examining the end connectors, measuring pin wear with practiced eye. His silence spoke volumes. German tank crews across the Italian front had been capturing and using American tanks when their own vehicles broke down, and the reports filtering back to maintenance units all mentioned the same bewildering characteristic. Sherman tracks lasted far longer than German tracks under identical conditions. The mathematics of track durability seemed to operate under different physical laws for American vehicles. A Panther track assembly, built with German precision engineering and metallurgical expertise, required replacement after roughly 400 to 600 kilometers of mixed terrain operation. A Tiger's tracks, even more precisely manufactured and expensive to produce, lasted perhaps 800 kilometers before pin wear and guide horn damage forced replacement. The Sherman tracks that Richter now examined appeared to have covered well over 1,000 kilometers, possibly 1,500, based on the wear patterns he could identify. This single knocked-out tank represented a broader pattern that German armoured forces had been documenting with growing unease since the Tunisia campaign. American track systems, built using design principles and materials the Germans considered inappropriate for military applications, consistently outlasted German tracks that embodied what Wehrmacht engineers believed represented optimal armoured vehicle engineering. The fundamental assumptions underlying German track design were being challenged not by superior German technical knowledge being surpassed, but by American automotive manufacturing principles applied to military requirements producing results German precision engineering could not match. Orchestrated historical narrative contrasting engineering philosophies and durability. Good start. I'm establishing the scene with specific details: date, location, serial number, personnel names, and introducing the central irony, German precision engineering being outdone by American wasteful design. Now I need to continue building the context about why tracks matter so much and what German engineering believed about proper track design. The strategic significance of track durability extended far beyond simple maintenance convenience. In armoured warfare, operational mobility determined whether units could execute their missions. Tanks immobilized by mechanical failure became static pillboxes, losing the offensive capability that justified their enormous resource investment. Track failures represented one of the most common causes of German tank immobilization across all fronts, often exceeding combat losses in some units during extended operations. A Panzer battalion advancing 200 kilometers to reach an attack position might arrive with 30% of its vehicles sidelined by thrown tracks, worn pins, or damaged guide horns. Maintenance crews would spend critical hours replacing track assemblies using scarce spare parts shipped from factories operating under increasing Allied bombing pressure. Meanwhile, American armored battalions covering similar distances arrived with negligible mechanical losses, their Sherman tracks requiring minimal attention beyond basic tension adjustments. German track design philosophy had evolved through years of careful engineering analysis and combat experience. The Panther tank, introduced in 1943 to counter the Soviet 34, featured interleaved road wheel arrangements that distributed the vehicle's 45-ton weight across overlapping wheels. This system provided excellent ride quality and protected the suspension, but created a track support structure of remarkable complexity. The tracks themselves consisted of precision-machined steel links connected by hardened pins, designed to exact tolerances that required specialized manufacturing equipment. German engineers believed this precision approach represented optimal engineering practice. Tight tolerances meant maximum strength from minimum material. Hardened steel provided superior wear resistance compared to softer metals. The entire system reflected decades of German mechanical engineering tradition, emphasizing theoretical optimization over practical manufacturing considerations. This philosophy had produced some of the most technically sophisticated armored vehicles in history, machines that German crews took fierce pride in operating. But theoretical optimization created vulnerabilities that combat conditions ruthlessly exposed. The Panther's interleaved road wheels trapped mud, snow, and debris between the wheels during operations. In winter conditions on the Eastern Front, this debris froze solid overnight, completely immobilizing vehicles until crews could thaw the accumulated ice using blowtorches or fires built beneath the hull. The process consumed hours and exposed crews to enemy fire in forward positions. Some Panther units on the Eastern Front reported spending more time thawing frozen road wheels than actually engaging enemy forces during the winter months. The track links themselves, manufactured to tight tolerances using hardened steel, proved brittle under impact. A track striking a large rock or obstacle at speed could crack, forcing immediate replacement of the damaged section. The hardened pins connecting the links wore through normal operation, elongating their holes in the track plates until the tracks could no longer maintain proper tension. Once pin wear reached critical levels, tracks would separate during operation, stranding vehicles until crews could effect repairs using specialized tools and replacement components. Tiger tanks, even more heavily engineered than Panthers, employed tracks 900 mm wide to distribute their 57-ton weight. These massive track assemblies required enormous quantities of scarce alloy steel, each track assembly weighed approximately 2,000 kilograms, making field replacement a grueling task requiring multiple crew members and several hours of hard labor. The guide horns that centered the tracks on the drive sprocket wore rapidly under the tremendous loads, with some Tiger units reporting guide horn replacement necessary every 300 to 400 kilometers. German field maintenance units documented these track durability problems in exhaustive detail through 1943 and 44. Reports from every front described similar patterns. Tracks failing at predictable intervals, requiring scheduled replacements that consumed scarce spare parts and maintenance time. Units planning operations had to factor track replacement into their logistics calculations, assuming a certain percentage of vehicles would need new tracks during any extended movement. This maintenance burden became part of the accepted reality of German armored operations. Then American forces landed in North Africa, and German tank crews encountered the Sherman for the first time in sustained combat. The initial assessments focused on what German analysts expected to find: inferior armor protection, adequate but unimpressive firepower, and typical American industrial mass production, visible in the tank's straightforward construction. German intelligence reports noted the Sherman's relatively thin armor and its 75mm gun, comparing both unfavorably to the latest German tank designs. But frontline troops began reporting observations that contradicted these paper assessments. Shermans kept moving when German tanks bogged down. They covered distances that should have required track replacements without stopping for maintenance. Captured Shermans pressed into German service, with their American tracks still installed, operated reliably for hundreds of kilometers before requiring any track work. These field reports accumulated through the Tunisia campaign, creating a pattern that maintenance specialists couldn't ignore. The Sherman track system embodied design principles fundamentally different from German approaches. Theoretical optimization through precision manufacturing and hard materials, American designers applied automotive industry mass production principles to create tracks that were easily manufactured, simple to maintain, and remarkably durable under field conditions. The American approach accepted what German engineers would consider crude tolerances and wasteful material usage to achieve practical results that German precision engineering couldn't match. The basic M4 Sherman used the vertical volute spring suspension system, abbreviated as VVSS, featuring 6 small road wheels per side, with simple vertical spring bogies. The track itself consisted of steel skeleton links with vulcanized rubber blocks bonded to the outer surface. These rubber track blocks, approximately 83 mm thick when new, provided the contact surface with the ground. German engineers had examined similar rubber block track designs before the war and dismissed them as unsuitable for military service, believing the rubber would deteriorate rapidly under combat conditions. The American rubber compound proved far more resilient than German estimates predicted. The rubber blocks absorbed impacts that would crack hardened steel links, flexing and rebounding rather than fracturing. When individual blocks wore down or damaged, crews could replace single blocks in the field, using basic hand tools, a repair taking perhaps 30 minutes compared to the hours required to replace an entire damaged German track section. The rubber also provided superior traction on ice, mud, and loose surfaces compared to bare steel, giving Shermans mobility advantages in poor conditions where German tracks struggled. The track pins connecting Sherman track links used a design that prioritized ease of field maintenance over theoretical strength optimization. The pins were removable using a sledgehammer and drift punch, tools available to any tank crew. German track pins, by contrast, often required specialized pullers and presses to remove, forcing crews to call up rear echelon maintenance units for track repairs that Sherman crews handled themselves. This maintenance accessibility meant Sherman crews could execute track repairs in forward positions without waiting for specialized equipment, keeping vehicles operational through repairs that would have sidelined German tanks for days. Spring 1944 brought expanded documentation of Sherman track performance as German forces retreated across Italy and faced renewed Soviet offensives on the Eastern Front. Captured American vehicles pressed into German service provided direct comparison opportunities, with German crews operating both Sherman and German tanks in the same units under identical conditions. These mixed formations generated detailed comparative data that appeared in unit maintenance logs and after-action reports. The Second Hermann Göring Panzer Division, operating in Italy during the Anzio campaign, captured several M4 Shermans intact during counterattacks in February 1944. The division's maintenance company, led by Hauptmann Friedrich Weber, incorporated these captured tanks into German combat formations alongside the division's own Panthers and Panzer IVs. Weber, a career logistics officer with engineering training, maintained meticulous records comparing maintenance requirements across the different tank types operating in his division. Weber's maintenance logs from March through May 1944 documented a pattern that confirmed what frontline crews had been reporting informally. The captured Shermans in German service required track maintenance approximately 1/4 as frequently as the Panthers operated by the same division. A Sherman might cover 1,200 to 1,500 kilometers before needing track replacement, while Panthers in the same unit needed new tracks every 400 to 500 kilometers. The disparity wasn't subtle or marginal. It represented a fundamental difference in track durability that had immediate operational implications. The rubber track blocks on the Shermans wore gradually and predictably, with crews able to visually assess remaining service life by examining block thickness. German steel tracks wore through pin elongation and guide horn damage, failures that could occur suddenly without warning, leaving vehicles stranded during operations. Sherman crews could plan track replacements during scheduled maintenance periods. German crews faced unexpected track failures that disrupted operations and forced vehicles to drop out of formation unexpectedly. Weber's reports circulated through Wehrmacht logistics channels, reaching the Army Ordnance Office in Berlin and technical staff at the Kummersdorf, proving grounds where captured Allied equipment underwent systematic evaluation. The findings corroborated testing data that German engineers had accumulated from multiple captured Sherman variants. The track system, dismissed by German designers as unsophisticated and wasteful, delivered practical performance that exceeded German precision-engineered systems across every meaningful metric except theoretical material efficiency. The comparison extended beyond simple durability measurements to encompass the entire support infrastructure required to maintain track operations. German track production consumed enormous quantities of specialized steel alloys and required precision manufacturing equipment operating to exacting tolerances. Each Panther track link required multiple machining operations using specialized tooling. The interleaved road wheel system demanded precision ground wheels, assembled with careful attention to bearing clearances and seal integrity. The complete system represented German engineering at its most sophisticated, combining metallurgical expertise with advanced manufacturing techniques. American track production, by contrast, leveraged existing rubber, manufacturing capacity, and straightforward steel fabrication, requiring far less specialized equipment. The rubber blocks bonded to Sherman tracks came from the same tire industry that produced millions of automobile and truck tires annually before the war. American industry simply scaled up existing processes to military requirements without developing entirely new manufacturing capabilities. The steel track skeletons required basic stamping and welding operations within the capability of numerous American manufacturers, allowing production to be distributed across multiple facilities rather than concentrated in specialized factories. This manufacturing flexibility provided strategic advantages that complemented the track system's superior field durability. When Allied bombing campaigns targeted German tank production, they could inflict disproportionate damage by hitting specialized facilities producing critical components. A successful raid on the handful of factories manufacturing Panther tracks could halt tank production across multiple assembly plants. American Sherman track production, distributed across dozens of facilities using common industrial processes, proved far more resilient to disruption. The rubber blocks themselves became a subject of particular fascination for German engineers analyzing captured Sherman tracks. German rubber industry, cut off from natural rubber supplies by Allied blockades, relied on synthetic rubber compounds that proved inferior to natural rubber in many applications. The synthetic rubber available to German industry became brittle at low temperatures and degraded rapidly when exposed to petroleum products. These limitations made German engineers skeptical of rubber components in military vehicles, reinforcing their preference for all-metal track designs. American rubber technology, benefiting from decades of civilian automotive industry development and access to natural rubber supplies through 1942, produced compounds vastly superior to German synthetics. The rubber blocks on Sherman tracks maintained flexibility across temperature ranges from Arctic cold to desert heat. They resisted petroleum contamination that would have destroyed German synthetic rubber. Even when American forces lost access to natural rubber supplies after Japanese conquests in Southeast Asia, American synthetic rubber programs produced compounds matching or exceeding natural rubber performance in most applications. Field reports from the Eastern Front in summer 1944 provided additional evidence of Sherman track superiority under the most demanding conditions. Soviet forces, equipped with thousands of Sherman tanks delivered through Lend-Lease, employed these vehicles alongside their own 24-Dreißig production in massive armoured operations across Ukraine and Belarus. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. German units facing these offensives encountered Shermans that had clearly covered enormous distances from railheads to the front, often several hundred kilometers across poor roads and cross-country terrain. The captured Sherman tracks, examined by German maintenance units after battles, showed wear patterns consistent with extensive use, but still possessed substantial remaining service life. German crews reported instances of pursuing retreating Soviet columns and encountering abandoned Shermans with mechanical issues unrelated to tracks, the track assemblies still intact and functional after distances that would have destroyed multiple sets of German tracks. These observations, documented in unit intelligence summaries and passed up through command channels, confirmed that Sherman track durability represented a genuine engineering achievement rather than isolated examples or propaganda exaggeration. Autumn 1944 brought the Western Front back into sharp focus for Wehrmacht forces as American and British forces pushed through France toward Germany's borders. The Ardennes offensive in December, Germany's last major counterattack in the West, produced another wave of comparative data as German units fought alongside and against Sherman-equipped formations under identical winter conditions. The operation, launched through the densely forested and mountainous Ardennes region in Belgium, tested both German and American track systems under severe stress. German Panther and Tiger units advancing through the Ardennes experienced catastrophic track failures from the operation's first days. The narrow, winding roads forced tanks off pavement onto soft shoulders and through rough terrain that exceeded peacetime training ground conditions. Tracks broke, pins wore through, and guide horns sheared off at rates that overwhelmed German maintenance capacity. Some Panther battalions reported 50% of their initial strength immobilized by track failures within the first 3 days of the offensive, before significant combat engagement. The American forces defending the Ardennes and counter-attacking into the German penetration operated Shermans under identical conditions with dramatically lower mechanical failure rates. German intelligence officers interrogating captured American tank crews specifically asked about maintenance procedures and track replacement schedules, trying to understand how American vehicles maintained operational capability under conditions that crippled German armor. The captured tankers described track maintenance as routine and infrequent, with most crews never having replaced tracks in months of combat operations. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe.